Hi everyone, welcome to the last chapter of this whole entire physics syllabus, okay? Electromagnetic induction. Now, this chapter is very important, okay, because it starts off the entire generation of electricity era in our modern civilization. Okay, let's begin. So Faraday, okay, and lenses were the two previous physicists that discovered this phenomena back in their days. So what they did was, okay, basically they experimented on how to generate electricity. And this is the way they did it. So they coil out wire. So they actually coil wire, something like electromagnet, but there is a difference. So they have got this wire coiled up. And then what happened is that it's coiled around an iron core, obviously to concentrate the fuse if there's any. So it's just wire wound around this iron core. But this is connected to this device called a galvanometer. Now this galvanometer is not a battery, so it cannot generate current on its own. What this does is that this galvanometer is a current sensing device. It senses current. How does it sense current? Well, it works from this needle. If I've got current coming here on the right to the left, the needle is going to point left. If my current is going to go from this direction left to the right, then this needle is going to turn right. So this needle is just turning in the direction of current. Okay, it's just turning in the direction of current. It's not an emitter, hence it does not give a value. It doesn't. Okay, so they have got this wire connected to this galvanometer. Okay, now what then they discovered is that there's a very interesting phenomenon. If they have a magnet on the right side, and you know magnets generate their own invisible magnetic field. Okay, this is a magnet. They discovered that when this knob goes approaching to this coil, what interesting thing happened was that this side of the coil would generate and induce north. Okay, it's very interesting. When this north comes, it is known to repel that. Okay, and they wanted to test this further. What happens if they have a southern state? Well, the same thing occurs. If the south comes approaching to this coil, the same thing occurs, and induced north will be produced at this end to repel this magnet. That's point number one. Okay? Now, you may ask, what happens if instead I do the reverse? If this north magnet is now withdrawn away from this coil, well, the interesting thing happens that now this part of the coil, okay, want to attract back, and it forms an induced south on this end. Okay? And what happens if I reverse it? Instead of this north withdrawing away, okay, I have got a south here. So instead of that, if I have got a south that withdrawn away, what happens? This part, you have guessed it, will be induced north. Now, I'm going to create this analogy so that you can easily remember. Now, this is very interesting because you realize that as this withdrawn away, there will be opposite to hold it back. Now, this is something very true, like in relationship. So, if one party goes away, the other party will pin for that person. So, opposite. Okay? Then, what happens is that if this is applied to the former case, like when north comes, and what happens is that this person, let's say you're advancing against towards the lady that you're interested in. If this person advances too fast, what happens is that the lady is going to reject it. Okay, so it's very similar to relationships. So when one party goes very strongly against the other, then there will be instant repulsion, and when the other starts to withdraw away, then there will be attraction of sorts. So this works in relationship too. Now let's investigate further. Okay, so let's say for example, okay, I got a coil here. The magnet goes to the left. So you know from that analogy I taught to you about, if north goes approaching to this coil, that will induce north. okay, at this end. Now, because it's induced north at this end, okay, we know that there's current, okay. So, according to the method I taught you, this perspective is that there is a current going anti-clockwise. So, in this way, anti-clockwise means, okay, from here, it's going to go like that, okay. So, it's going to go like that, okay. So, it was going to go like this. So, let's check. Okay, current is going to go like this anti-clockwise. In this perspective, going to. So, what happens that my needle is going to turn to the right now. So let's try again. It is north anti-clockwise. It goes like that, out, and hence it goes here, and then it turns my needle to the right. Okay, so my current is confirmed correct. Now let's go deeper than that. So initially, when my coil is here, why do you have a current going around like that? Well, initially, this coil here, let's give it more a mathematical understanding of this topic. So initially, this coil wire will cut this in this B field. I've drawn the B field like that north to south, and some of the ones for the further away ones. So you find that this coil wire, okay, you see carefully, you see that this coil wire, okay, this coil wire and this wire cuts one magnetic field line, two magnetic field line. So at this stage, time 1, you will cut 1, 2 field lines. So let's write it down. So flux cut equals to 2 initially. Okay, this is when this coil is at this position. Now, I'm going to move the magnet in. North is going to go in, and look what happens to it when I draw the second configuration. So, if I draw the second configuration, let's say so on and so forth. So, what happens is that now, let's look at how many field is going to cut. Okay, reproducing the B field lines just now. Now, this wire is going to cut, okay, 1, 2, 3, 4, 5, 6. So, my flux that I cut at this time equals to 2 stage. It is the second stage in which it has moved in, okay? I mean, as this magnet has moved further in, okay? So, flux cut later, this will be 6, okay? Now, instantaneously, you know that by moving this magnet towards the coil, I'm cutting more magnetic field lines. This cutting of magnetic field line is the critical bit. It actually releases the magnetic energy into electrical energy. That's what they found. So once this metal wire cuts across this invisible magnetic field, it releases the magnetic energy to electrical energy. Okay. Not only that, okay, they found that the more it cuts, the more the bigger the current going around. Okay, the more the current going through the circuit here. And they found this, that the voltage generated, the EMF generated, they found, okay, is proportional to the change, okay, flux divided by time. So, meaning to say, in very small amount of time, I cut a lot of flux, okay? Change of the flux linkage should be the right term here, okay? Change of flux linkage. Okay, in short time, I cut a lot of flux linkage. I have got greater voltages of the EMF generated. So let's look back at this example that I have here. Initially, I cut 2, then this magnet moved in, and cut 6. 1, 2, 3, 4, 5, 6. And let's assume I give it some number. If I'm able to move this magnet to the right fast in, and I take, let's say, for example, 0.2 of a second. Okay? So I can calculate the voltage that is going to be generated like this. So the voltage should just be EMF. If it equals to change flux over time, and that will be from 2 magnetic fields cut to 6, that will be 4 divided by 1 second. then that will be what? I will have this instead. I'll have got 20 volts being generated. So that was what they found. Okay, that the EMF is proportional to how fast I move a magnet, and then this coil wire will cut this DC. How fast it is, the faster you are, the more voltage you generate. Okay, so now let's look at how the previous idea is applied to generating electricity. So we know that if I got wire that cuts a B field, it generates current. Okay, so if I have got a wire concentrated in a concentrated B field and I cut it, I've got more current. Okay, so that's the basis for this generator circuit. Now this is called generator circuit. I've got an armature, I've got battery, I've got magnets, not battery. Magnets and armature. Note there isn't a battery here in the circuit. Okay, there is no battery here. You take a look. This is a resistor, and the whole thing goes to a household or resistance load. It has no battery. Okay? We are going to create electricity from this circuit. So, first thing to take note for this generator circuit is that, number one, we choose a direction of rotation. So let's say, for example, this armature, I deliberately turn this way. Let's say I choose to turn in this direction. I mean, in a clockwise direction. Let's see what happens. So I choose a rotation that I want to apply force in to make it rotate clockwise in this regard. Now, I want you to look at the way I'm doing it. So let's continue. So I am applying a force outwards. I use my hand physically turn so that this thing turns clockwise. Alright? Now, when this thing turns clockwise, I use my right hand. Okay, because this is generator. Remember, generators for right hand. Okay, motor left hand, generator right hand. So applying this, force is upwards, field point to the south, and current. Okay, current. Okay, this current goes in applying the right hand. Now this current is induced, so I have to write it is induced force. It's force. Okay, it wasn't there. So this current is going to go around. This induced current is going to go around. Okay, the circuit in this way. Okay, so my current is going to go in this direction. Now please take note of the current direction because later, okay, there will be something I want you to see. So when I turn here, my current goes in a clockwise direction. Okay, so this is for stage 1. Okay, now I'm going to turn it and draw a second stage. Oh, but before I do the second stage, I label here AB, and then here this is BC. Later AB is going to go to the right, and this whole thing is going to reverse, just to let you know first. So now I've drawn another picture of what happens when AB side of the armature goes to the right side. Now, the construction of these rings is the more difficult part of both the motor and generator. But it's very interesting for generator because once the AB goes over, it's not so simple. Once this guy goes over, you find that this part will go over to the side instead of connecting to the left, it now connects to the right. And then I've got this portion here. And for some reason, okay, this is the way it is. So CD is now connected to the side here now. Remember just now this was pointing to the right and then it takes from the left. So I'm trying to draw this for your benefit. Now, is there a difference? Yes, there is. Look carefully. So force, field, current. Now force is applied in the same direction of turning as before. Force down is down. So force down, field, current. Now you realize that here, according to the right hand rule, the Flemish right hand rule is as per normal. There's nothing. So force, field, current is going to go to it's going to go in this direction. Okay? But the interesting thing is this setup because of the rings. So you find that here, the current is going to come by this way. It goes up, come by this way, right? And then here, here, and continue. Realize my current has already reversed in direction. Okay, my current